Welcome to the Greek Ship Corrosion channel. My name is Maryam. I'm a researcher in the field of corrosion and protection of materials. Chapter 2, Section 8, Thermodynamics of Electrochemical Reactions. In this video, solving 4 practical examples using Nernst equation is presented. The main reference is Fundamentals of Electrochemical Corrosion, ASM International. The Nernst equation enables the determination of the cell potential under non-standard conditions. The standard state for reactants and products in the generalized electrochemical reaction is pure solid for solid species, 1 atmosphere pressure for gas species, unit activity approximately unit molality for ionic species. For example, the activity of Mn plus equals 1 and the temperature equals 25 degrees Celsius or 298 Kelvin. Nernst equation usually focuses on the effect of concentration on half cell potential. In our slides, E shows general case of potential and E prime shows potential in the case of no current passing, that is at equilibrium. The Nernst equation relates the instantaneous potential E to the standard potential E naught and the reaction quotient Q. E equals E naught minus 0.0592 volts per N logarithm of Q at 298 Kelvin. When all reactants and products are in their standard states, Q equals 1 and E equals E naught. When the reaction is at equilibrium, Q equals K and E equals 0. K is the equilibrium constant. The reaction quotient is available on this channel, slide number 231, the video titled Chapter 2, Section 7. This is Nernst equation, in which X, Y, and Z are symbolic representative of the important species involved in the reaction. The mathematical sentence in the numerator is the product of the activities of the species in the oxidized side, the side showing electrons produced, each raised to its stoichiometric coefficient, nu I. The mathematical sentence in the denominator of the fraction has similar meaning for the reduced side of the reaction, and N is the number of moles of electron produced or consumed per unit of the half reaction. Example number 1, oxidation of nitrous acid or reduction of nitrate ion. HNO2 plus H2O equals NO3 minus plus 3H plus 2 electrons. The left side is the reduced side. The non-standard potential of this half cell equals the standard potential of this half cell plus RT over 2F times ln of the activity of NO3 minus times the activity of H plus raised to 3 over the activity of HNO2. Standard reduction potentials in millivolts versus standard hydrogen electrode are shown in this table. O2 plus 2H2O plus 4 electrons equals 4 OH minus E naught equals positive 401. O2 plus 2H plus 2 electrons equals H2O2 E naught equals positive 695 millivolts. 2NO3 minus plus 4H plus 2 electrons equals N2O4 plus 2H2O. E naught equals positive 803. NO3 minus plus 3H plus 2 electrons equals HNO2 plus H2O. E naught equals positive 940. O2 plus 4H plus 4 electrons equals 2H2O. Standard potential equals positive 1229. Example number 2. ZnZn2 plus half cell. Consider a metal ion half cell Mn plus M electrons equals M and the Nernst equation. R is 8.3145 joules per mole per Kelvin, that is the universal gas constant, and T is 298 Kelvin, F is 96,485 coulombs per mole of electron, the natural logarithm of A or ln of A equals 2.303 logarithm of A, and 1 volt is 1000 millivolts, then the non-standard potential equals the standard potential plus 8.314 times 298 times 1000 over m times 96,485 times 2.303 logarithm of the activity of Mn plus. That is the product of the activity coefficient times the concentration of the Mn plus cations. Non-standard potential equals standard potential plus 59 over m logarithm of the activity of Mn plus. If Zn plus Zn half cell reaction is considered, then the standard potential equals negative 763 millivolts versus standard hydrogen electrode, and Zn2 plus 2 electrons equals Zn. The non-standard potential equals negative 763 plus 59 over 2 logarithm of the activity of Zn2 plus. If the activity of Zn2 plus equals 1, then E prime equals negative 763. If the activity of Zn2 plus equals 10 to negative power of 2, then the non-standard potential of this half cell equals negative 822. If the activity of the cations equals 10 to negative power of 4, the non-standard potential is negative 881. And if the activity of Zn2 plus equals 10 to the negative power of 6, then the non-standard potential equals negative 940. Dependence of metal reaction equilibrium potential on metal ion activity for zinc. By decreasing of metal ion activity, the redox potential is decreasing too. That means the metal shows more tendency for corrosion in the industrial solutions in which the activity of the metal ion is less than 1 or unit in comparison with standard state. Thank you for your attention. For more convenience, the other two examples are presented in the next video.